Welcome to The Explainer. Today, we're tackling a classic calculus puzzle. How do you find the exact area of a strange, curved shape trapped between two different lines? It's a question that unlocks some incredibly powerful ideas, so let's dive in. You know, geometry class gives you all these neat formulas for squares and circles. But what happens when you run into a shape like this? It's bounded by two totally different functions, f of x and g of x. How in the world do you find the exact area of that shaded region? So here's the game plan. We'll start with the basic intuition behind it all, then we'll build the main top minus bottom formula. After that, we'll see what to do when things get messy and the curves cross over. Then I'll show you a really cool trick, a sideways glance, to solve tough problems. And finally, we'll talk about why any of this actually matters. All right, section 1. Before we even think about formulas, let's just use our intuition. How would you even begin to measure a shape with squiggly, unpredictable edges? The big idea here is actually pretty genius. Instead of trying to measure this whole weird blob at once, just slice it up. Imagine cutting it into a ton of super thin vertical rectangles. I mean, we all know how to find the area of a rectangle, right? It's easy. Height times width. So if we could just find the area of every single one of those little slices and add them all up, we'd get a really good approximation of the total area. Okay, so here's the clever part. We don't need to get bogged down thinking about a million different rectangles. Let's just zoom in and look at one of them, a single, typical, representative rectangle. The idea is, if we can figure out a rule for the area of this one rectangle, we can apply that rule to any rectangle in that space. And then, well, that's where the magic of calculus comes in to add them all up perfectly for us. So let's look at that one rectangle. What's its height? It's actually way simpler than you might think. At any given point along the x-axis, the height is just the y value of the top curve, f of x, minus the y value of the bottom curve, g of x. That's it. That simple subtraction gives us the precise height of our slice at that exact spot. And that one simple idea, top minus bottom, that's the key that unlocks the whole thing. It leads us straight to the big, powerful formula for finding the area between any two curves. And here it is. This is what it all boils down to. You see that integral sign? That's the powerhouse of calculus. It's the tool that's literally built to do one thing perfectly: add up an infinite number of infinitely small things. So when we integrate our height, our f of x minus g of x, from our starting point A to our endpoint B, we're telling the math to add up the area of every single one of those tiny little rectangles. And that gives us the exact area. No approximation, the real deal. Okay, enough theory. Let's put this thing to work. We've got this example here. We need to find the area of that shaded region squished between that parabola on top and the straight line on the bottom. All right, first things first, we need our limits of integration, right? Our a and b. The problem doesn't just hand them to us. But if you look at the graph, it's pretty clear where our area starts and ends. It's right where the two curves intersect. So how do we find those spots? Simple. We just set the two equations equal to each other and solve for x. A little bit of algebra later, boom, we find out they cross at x equals -2 and x equals 6. Those are our bounds. Awesome. Now we've got everything we need to build our integral. We're going to integrate from -2 to 6. And what goes inside? You guessed it, top function minus bottom function, the parabola minus the line. Simple as that. And from here on out, it's just turning the crank on the calculus machine. You find the antiderivative, you plug in the 6, you plug in the -2, you subtract, and what do you get? The exact area is 64/3. I mean, how cool is that? Not an approximation, not a guess, the perfect answer for that weird curvy shape. Okay, that's great and all, but top minus bottom works like a charm when one function is always on top. But what happens when they do a little dance and switch places? What do we do then? And this right here is the perfect example. Check out the area between sine and cosine. In that first chunk, R1, cosine is the top function. But then they cross, and in the second chunk, R2, sine is on top. Suddenly, our super simple top minus bottom rule gets a little tricky, doesn't it? So what's the fix? It's actually pretty straightforward. You just chop the problem apart. You find that intersection point and treat it like a boundary. You set up one integral for the first region, where cosine is on top, and a second integral for the second region, where sine is on top.
You solve them both, add the answers together, and you've got your total area. You just break it down into smaller, manageable pieces.
All right, now I want to show you something really cool. It's a powerful trick for when the standard way of doing things gets, well, really annoying. Sometimes all you need is a change of perspective to make a hard problem suddenly become easy.
Okay, take a look at this shape. We've got a problem, right? The top function isn't consistent. For the first part of the area, the parabola is on top, but for the second part, the straight line is on top. That means, just like before, we'd have to set up two separate integrals and add them together. It's doable, but
I mean, that just feels like a lot of work for a shape that looks pretty simple. So the question is, isn't there a smarter way to do this? Can't we solve it with just one integral?
And the answer is yes. This is the big aha moment. What if we just turn our heads sideways? Instead of slicing the area up with vertical rectangles, what if we sliced it with horizontal ones? All of a sudden, everything changes. Now, no matter where you draw your horizontal slice, you always have the same function on the right and the same function on the left. The whole who's on top problem completely disappears. So this gives us a totally new strategy. Instead of integrating with respect to x and thinking top minus bottom, we can integrate with respect to y and think right minus left. The only thing we have to do is a little bit of algebra first. We need to solve our equations for x so they become functions of y.
So let's go back to our problem. We rewrite the functions in terms of y. The curve on the right becomes x equals 2 minus y. The curve on the left becomes x equals the square root of y. Now we integrate along the y-axis from 0 to 1. And look at that. We get the same answer, 5/6, but we did it in one clean integral. So much easier.
Okay, so we've picked up some seriously powerful tools here. But let's take a step back. Why does any of this matter? Why is measuring these weird shapes so important, not just in calculus, but, in the real world? All right, let's wrap this up. What are the big takeaways? First, the basic move. Integrate top minus bottom. If the curves cross, no big deal. Just split the problem into pieces. And don't forget your secret weapon. Sometimes it's way easier to think right minus left. But here's the real kicker. This isn't just a math exercise. This is a foundational skill. This is how engineers calculate the volume of complex parts, how physicists find the center of mass of an object, or how you'd figure out the force of water pushing against the curved wall of a dam. It's a tool for measuring the real, messy, curved world around us. And, this whole idea of slicing things up, it naturally leads to the next big question. We figured out how to find a 2D area by slicing it into 1D lines. So, what happens if we take a 3D object and slice it up into 2D areas? How could we use that to find its volume? But that's a story for another explainer.